be able to hand over to our speaker tonight.
You ready? Okay.
Yeah, our speaker tonight from NOC, the Professor Ivan Haigh.
So first of all, thank you all very much for coming. I personally wouldn't come out for an evening to hear myself speak, so it's always humbling when other people do. Second, Nigel asked me to talk about something, I can't even remember what it was. I sent him an email with what I was going to talk about. When I started preparing this 3 days ago, I couldn't remember what I had promised to talk about. So the title might be different, but hopefully it's something vaguely sea level related that you're expecting. I'm not going to talk much about coastal flooding. I'm going to focus more on the sort of long-term, slow, century-scale changes in sea level. So just by way of introduction, I did my degree here. I graduated in 2001. I studied oceanography with maths. I then went on and worked for the port. I worked for Associated British Ports for 5 years in their research arm, mostly doing a lot of work on port development, coastal flooding. And it was during that time I got very interested in sea level. I came back to the university, I went to civil engineering and I did a PhD there on sea level rise actually and coastal flooding around the UK. I then worked as a researcher in Western Australia for 3 years before coming back to the university as a lecturer. I've been at the NOC for about 6 years now, more recently as an associate professor in the last couple of years. Okay, and so I've spent the last, I guess, probably since 2001, so about 17, 18 years now, looking at sea level, and it's really my passion. I love anything to do with sea level. Now, I always laugh a little bit when I hear the word sea level. You look in a dictionary, you all know what the sea is. I don't need to define that. But level implies that something is flat. But the sea is never, ever flat. Okay, I was lucky to live by the sea. I don't live very far now, but in Australia I lived on the beach and I swam in the sea every single day for 3 years. And other than one perfect night where the sea was just mirror calm, the sea is always moving. It's never ever flat. On lots of time and space scales you get all sorts of movement. Now, what I do with all of my students, it's a little bit blurry, but what I do with all of my students is I set them a little exam. And one thing I want to know about this evening is I don't want to just sit here and talk for 30 minutes. You guys have to talk, okay? So I'm expecting some audience participation, okay? So just be aware of that. I might pick on you as well. Okay, so please talk. It's not just going to be me talking. If you've got a question, don't bother waiting for the end. If it's something pressing, just ask me in the talk and interrupt me and I'll answer it there and then. Obviously, you can wait to the end as well. Okay, so what I do with all of my students is I have time on this axis, okay? So we have seconds over here through to millions of years over here. On this axis, I've got space, so a millimetre, right through to 40,000 kilometres, which is the whole Earth. Okay, so across all of these time and space scales, sea levels vary. What happens down here? Waves. Right down at this end. Ripples, turbulence, that sort of thing. So right down at that end we have turbulence, okay? These are microscopic little ripples that you see if you blow over a cup or something. Okay, what do we get a little bit higher up? Waves. Very good. We get waves and seiching. Seiching is a term after someone who lived in Switzerland, and he noticed that when wind blew over a lake, if the wind suddenly stopped, the lake would oscillate for several days. That's called a seiche. And you do get that in some harbours, that kind of nice, gentle oscillation. Okay, what else? What do we have this saying? Tides. We get a frequency of movement before tides. So we do have tides, but slightly earlier than tides.
Swell.
I include swell in waves. So with waves, you get locally generated waves, you get swell, which is further away. I've kind of clumped those all in with waves. What else do you get? Kills millions of people? Boxing Day? Tsunamis. Okay, so we have tsunamis there. Now notice with tsunamis are quite short-lived. Well, they can spend days propagating the ocean, but in terms of affecting the coast, they're quite short-lived, but they affect much larger stretches of the coastline. Then, oh, I gave that away, but then we get storm surges, and these are the movement of the sea caused by weather. We tend to get two categories of storm surges. We get tropical storms, which are hurricanes. So again, those affect quite large stretches of the coastline, but they tend to last for about 12 hours. Obviously, hurricanes go for several days, but they cross the coastline. They last for hours. What do we have next? You said it?
Oh, tides.
Tides, yeah. Now, tides, we have two main bands of energy. We have semi-diurnal tides, which is what we get here in the UK, 2 tides a day. We also get diurnal tides. Some parts of the world we only have 1 tide a day. In Western Australia, for example, in the Gulf of Mexico, you get 1 tide a day. And those tend to, so that affects the whole world. What do we get here? Affect the UK, affect the North Sea.
Double high water.
Well, I would lump that into as part of tides. But good, yeah, that's very good. What do we get here? That was a clue, tropical storms. We get extra tropical storms. So these are the sorts of things that affect the North Sea, the UK. They're storms, they tend to last about 2 days. They tend to be quite big as well. And then what do we then have up here? I'm not one of those people that gets uncomfortable with silence. I'm happy to...
Cataclysms?
What do you mean by cataclysms?
Catastrophes? I don't know. Collision of continents? I don't know.
Sea level changes due to ice ages.
Yes, yeah. So first of all, we have seasonal effects. We have things like El Nino sub-oscillation. The wind can blow on shore for 6 months, blow offshore for 6 months. That can raise the level of the sea. Here in the UK, sea levels change by 10 centimetres between winter and summer. As the water is cooler, it's warmer. So we get those seasonal effects. They tend to be quite small. Is there any way we can get this any less blurry? Then we have sort of climate change effects. And then right up here we have our glacial cycles, and I'll talk about it. So sea levels change by hundreds of metres with glacial strains. Is everyone tracking? Yep, everyone happy? Anything I'm missing? You want to throw in there?
What about through the channel, on the French side, the sea level could be higher than on the English side at certain times? Where would you classify that at?
Again, there could be lots of...
Because it acts like a river, you know,
yeah.
Going through it. It throws up the water onto the French coast.
Yeah, most of that is tides. As a tide comes in, Coriolis pulls it towards the right. But you could also get winds effects. If there's very strong onshore winds to the French, that could create a difference.
I was thinking more of currents.
Okay, ocean currents, that's a good one. Ocean currents tend to come in here. They tend to be more sort of seasonal. So you get very strong currents for part of the year, not strong. So I would probably put that in that sort of band there. Okay, so there's a lot of things going on here, and actually there's a lot more of sort of little processes, but I put them into the sort of main big processes. But actually, all of these different levels, there's only 3 fundamental things that change. Okay, I've got 3 beakers here. We've got the same water levels. There is actually only 3 ways you can change the level in that beaker. And all of those 3 things relate in part to this. There's only 3 ways you can change the level in that beaker. Okay, this place probably doesn't have a alcohol license, but I'm going to break that just for the time being. So here's a beer. Here's a cup. I'm going to pour the beer into the cup, and I'm going to pop that down there. It's got a little bit of a head. Let's put 2. There is only 3 ways you can change the level in that cup, okay? Now, don't be clever to start with, okay? Could someone, in the most simple, basic form, if you give a man or a woman a beer, most likely a man, they're going to change the level in that cup using one way. So don't be clever, don't just think of the first most basic way. And could someone come down
Yeah, they'll suck it up.
and demonstrate? Don't talk, please. both with your feet, come down and change the level in that cup. Okay, very good. What was your name?
Simon.
Simon. What did Simon do?
He added beer to the cup.
Yeah. Okay, I was expecting him to do the inverse of that, which is...
I've got work later.
You got work later. I was going to offer that you. Okay, so the first thing you can do is you can add or subtract. If that had been me, I probably would have subtracted, but he added. Okay, so one of the three fundamental things you can do at that level is you can add or subtract. You can add water, you can subtract. What else?
Displace.
Come down and show us. Don't shout it out.
Put your finger in it.
Yeah. This cannot end well. There you go. Okay, very, very good. Okay, fantastic. Okay, the other thing you could do, which would be exactly the same, is just kind of squeeze the cup. So this is Ed. So what did Ed do? What did he do to the water? Not water is incompressible, almost incompressible. So he didn't. It's very hard to compress water. So yeah, water is fairly incompressible. So he didn't compress the water. What did he do? He displaced. What's another word for displaced? He didn't. The water didn't change in volume. It's the same amount of water in there. Yeah, he changed the shape of the container. But what did he do to the water?
You replaced
Moved
the water.
That's the key thing. He moved it. Now I can't remember where move is. It's one of those. So I'm not going to bring it up next. So you can add or subtract, or you can move the water. There's various ways you could move water. You could blow wind and force water to one side of the basin. You can change the shape of the basin itself. You could put something into the basin. But fundamentally what you're doing is moving the water. What's the final thing you can do?
Temperature.
Very good. So how would we alter the temperature? Well, this is a paper cup, so we wouldn't want to do it, but we could put a lighter under there, we could put it in the freezer. Okay, so this is just my thinking, but those are the three fundamental things we could do. We can add or subtract, we can change the properties, or we can move the water. Okay? Changing the properties, you could change the salt content, that would affect the water level, but primarily you either heat or cool. Heat expands, it rises, cool, it contracts, it lowers. So actually, all of these processes are doing one of those three things. So what are waves doing?
Moving.
Just moving. What are tsunamis doing? Just moving. Tides? Moving. Climate change?
Temperature.
So climate change is actually doing all three. The world is heating up, oceans are expanding, ice is melting. So thermal expansion is changing the properties. Land-based ice is melting, it's adding volume. But also climate change can move, and people often forget that climate change can alter wind patterns, which might lower sea levels in some areas, increase it in others, and we'll look at that later. If anyone can think of a fourth, tell me, and I'll add it. But I've spent a long time thinking about this, so I don't think there is a fourth. So I think there's only those three fundamental things.
Where would you put air pressure then?
It's just moving. So water is incompressible, but what air pressure is doing, if you've got high pressure raises up, it sucks water in from other regions, it's not creating any extra water, but pressure is fundamentally moving water. So very good, pressure is one of the key changes, but I would put it under that move box. Okay, everyone tracking? Everyone happy? Okay. So what I want to do now is get on to talk about, I'm going to focus up here. I'm going to focus on the sort of longer term changes. I'm not going to talk about tides, I'm not going to talk about waves, I might mention flooding a little bit later, but primarily I want to talk about these slow century scale changes in sea level. And what we observe is over the last 150 years, After sea levels have been relatively flat for about 2,000 years, if you take the kind of average, if you average out all of these processes, if you just take the sort of mean everyday level, that's been rising. It's risen by about 20 centimetres. So what I want to do is really sort of talk about that and try and put that into a historic context as well. But first of all, why is it important to understand these baseline changes? What are the key things, what are the key implications of sea levels rising? That's a question.
Cost.
Cost of what?
Infrastructure losses.
So sea levels rise, it might affect coastal infrastructure, mainly through flooding or inundation. Very good. What else? What are the implications of sea level rise?
It reduces the land mass.
Yep, so it can reduce the land mass, very good, particularly sort of coastal wetlands, it can affect those. What else?
So environmental impact.
Yep, so
Coastal wetlands.
yeah, so coastal wetlands losing, that's fundamentally important. Wetlands are very important in a number of things. What else?
It reduces habitable areas, so population will have to move.
Yep, yep.
Change weather patterns.
Why would sea level rise change weather patterns? Just out of interest.
I'm not a scientist. But you mentioned, well, for example, how the weather, the whole weather moves across over open water.
Yeah.
And if you're increasing that space,
Yeah, then you can fundamentally change other things. Very, very good. Anything else?
Some lakes which are on a low level will become salty because they were...
Very good, that was the one. Yeah, sure. So I've got 5 main things that sea level does. One is, as sea levels rise, you need less extreme storms to give you the same high sea levels. So the first thing is it just inundates land, you've got storm damage to infrastructure. This is an estuary with an unusual shape. This is in Western Australia, but this is the red area is the area of land that will be inundated during a 1 in 1,000 year flood. But if we raise sea level by a metre, a significant larger amount of land will be inundated by that same event. So obviously sea levels rising, it can affect inundation, which has cost implications, affects the population. It's actually quite difficult to give an example because sea levels have only risen by about 20 centimetres. But this is a nice example here. This is called Sharp's Island, and it's located in Chesapeake Bay. Here, or it was located in Chesapeake Bay. In the 18th century, this island housed about 100 people. It had a farm, it had a little school, it had a few hotels, but a combination of sea level rising and land sinking, this was all that was left of the island in 1950. And even that has gone underwater now. So that's just one example where you can see even a small rise in sea levels has really affected an island. The next main consequence is wetland loss. Wetlands are very important for a whole range of reasons, regulating diseases, biodiversity. And what we find is as sea levels rise, this is in the US, in mainland, but you can see that these nice natural wetland creeks with sea level rising just gets lost. And those creeks are very important. They absorb carbon dioxide, they do a lot of things. We didn't mention this yet, but one of the key issues with sea level rise is coastal erosion. This is the Holderness coast, which is eroded by about 2 kilometres, even before sea level rising. But sea level rise kind of speeds that up. And sadly enough, I visited this coast, and a number of houses have gone off the cliff. People are still paying their mortgage off on the house, even though the house has gone off the cliff, which is really, really sad. Saltwater intrusion is one of the key issues, not so much in this country, but other countries. A lot of places have this freshwater lens, and this is very much the case with the Maldives and other low-lying atoll islands. And the concern is that sea level rises, salty water will get into this freshwater lens. So people often talk about sea level rise directly affecting small islands, but actually, even if the islands are still there, it might be that these freshwaters, the communities can't live there just because there's no fresh water, not so much because of the sort of storm surge damage, so an indirect effect. And then the final thing is raising water tables, and we see this a lot in the States, but as sea levels rise, lots of places have a sort of natural fresh water supply underneath. Sea level can push that whole supply up. And you see this in the States quite a bit, where certain towns are now, they're getting flooding in their basements just because sea levels are sort of pushing up that water table. So those are the 5 main key changes that we see. Now what I wanted to do was put sea level into the historic context. So before we talk about what sort of happened over the last 100 years, I want to look back longer term. And it's quite hard, we can't directly measure sea level longer term over several thousands of years, several hundreds of thousands of years. But we can measure sea level indirectly using a number of proxies. This is not my area, but I've just been involved in a £4 million grant with about 10 universities around the UK looking at this. So one thing we can use is salt marshes, and I'll tell you a bit about that in a minute. We can use archaeology. There's a number of sites around the world that are now underwater that weren't, and we can estimate how much sea level has risen. We can actually use speleothems. We can use stalactites, which I'll talk about in a minute. We can use coral reefs, because corals tend to follow where sea levels are. We can use geology, and we can actually use, a bit like ice cores, we can use sediment cores. So what happens with salt marshes is salt marshes tend to have different layers. There are species of plants. So down here you'll have a certain species of plants, and then you'll have a different species of plants where that are not covered by the tide. But what happens as sea levels rise, these salt marshes start moving backwards. And as long as sea levels have risen steadily, you can take a core down through the marsh. It's a bit like layers of sediment. And what you can do is you can count the number of these microscopic creatures. They're called forams. Each different sort of, near the sea you get certain types of these single cell organisms. As you go towards land you get different species. But what you can do is you can take a core and count these species and use that as sort of a proxy. It sort of tells you what sea levels might have been doing about 1,000 years ago. And there's a professor up in York who does a lot of work on this. With archaeology, there's a number of things you can do, but one of the things is these Roman fish tanks. It's a bit hard to see here, but the Romans in the Mediterranean, you can go and see these sites. They built fish dams very near to the sea where they kind of, it's almost like aquaculture, they raised fish in there. These dams are now underwater, and again we can get a pretty, we think these were built about 2,000 years ago, we can get a pretty accurate estimate of what sea levels were doing 2,000 years ago. Other things are marks. So James Ross Clark went to Tasmania and he carved a mark in a rock near to Hobart, which was an estimate of what mean sea level was at the time. One of my very close friends in Australia, John Hunter, spent about 3 years doing measurements here. But using that mark, it was put into the rock about 150 years ago. We can estimate how much sea levels have changed in that time. Now, speleothems are very interesting. What is it? Stalactites that hang down. Stalactites. What happens is, and stalagmites come from the bottom. What happens is stalagmites only form if there's air. If that cave becomes underwater, they can't form. But there's a number of caves in Bermuda which have stalagmites and now they're underwater. And a group in Oxford have got a very special mission to take these, and they form like tree rings, a bit like a tree ring. But what we can do is split these stalactites open and we can actually date these tree rings, and we can see when that stalagmite stopped growing, and that's an indication at that point that sea levels were at that level then. So again, we can use these as a kind of estimate. The other things we can do is corals. Certain species of corals live a certain distance underwater. They tend to be, corals mostly live within 15 meters of sea level rise. As sea levels rise, those corals kind of migrate, they need light. They die out. So again, we can drill into corals and estimate what sea levels, from dead corals, estimate what sea levels were like. Those corals now are sort of underwater. Again, we can use geology. This hill sort of indicates that probably at these points sea level was at all of these many sort of hundreds of thousands to millions of years ago. And another thing we can do is take sediment cores, particularly from the Red Sea. And again, we can date the levels. So all of these, they're not very accurate, but they give us an indication of what sea levels have been doing for tens of thousands of years. And what we find is down the bottom, this is what sea levels are like. And unfortunately, being geologists, they always plot things the wrong way around. This is present day. That's going back into time. But what we see is people talk a lot about climate change. I very much believe climate change is happening, but it's always good to put it in context. What we see that sea levels have varied by up to 120 meters over the last 500,000 years. And that very much relates to the ice ages. So when the world was covered by ice 25,000 years ago, sea levels were about 100 metres lower than they were today. And what we find is, going back in time, there's certainly 2 occasions. There's been 5 main ice ages, but there's been 2 occasions when sea levels have been actually higher than they are today in the past, under different climate change conditions. And the general theory is that these relate to Milankovitch cycles. We've got an expert on Milankovitch here, but Milankovitch cycles are small wobbles in the Earth's rotation, and those come in and out of phase, and that causes you to go to ice age and not ice age. But essentially, an ice age, when the world's covered by a lot of ice, all that water is sucked up from the ocean, stored in ice, so sea levels are a lot lower than today. When that melts, you go into an interglacial stage, then sea levels rise. But what we see is sea levels have changed by at least 130 metres. And if we zoom into the last ice age, and we can, all of these blue dots are information that we've got from corals. What we can see is 24,000 years ago, sea levels were a lot lower than they were today. Sea levels gradually rose. This meltwater pulse actually rose quite fast. But what we can see is then sea levels have stabilised. So in the last 7,000 years, sea levels have been fairly stable, and particularly in the last 2,000 years, sea levels have been virtually unchanged. And that's been brilliant because that's coincided with a massive growth in human population. And actually, I don't think human population could have increased so much with this fluctuation in sea levels. That steady period has helped civilizations develop, helped us build cities on the coast. But what we see is, certainly in more recent times, that's starting to rise. We would, without climate change, expect that to stay level and eventually to go into another ice age. And what we see is, this actually formed the North Sea. So this is what the UK looked like 20,000 years ago. So everything in blue is what was covered in water. This is what was covered in ice. So during the last ice age, everything up to about Birmingham was covered in ice. But what you can see is the North Sea was land. And then as sea levels rose, at about 15,000 years ago, the Irish Sea formed. About 12,000 years ago, water came into the English Channel, but we were still connected to France. And then we got a giant Brexit, the first Brexit. There, when England actually formed, that was about 9,000 years ago. And coming towards today, you can see the North Sea. But 10,000 years ago, we didn't have the North Sea. We were completely connected to the mainland. So that's really what's caused our island. Okay. Now, what I want to do is jump ahead to modern days. So I just wanted to give you the historic context. Sea levels have varied a lot, plus or minus 100 metres, okay? But in the last few thousand years, they've been relatively stable. So in more modern times, we have much more precise instrumentation. We have tide gauges. Around the UK, we have hundreds of tide gauges, 40 that are kind of run by the government, particularly to monitor sea level. We have satellites as well, can give us a very good indication of what is happening. How am I doing for time?
Two-thirds through.
Okay, now what we find is that we have extremely high confidence. So with that paleo stuff, there's a lot of uncertainty, there's a lot of, the measurements aren't particularly certain, but with tide gauges and satellite, we have much more confidence. We can measure sea levels to within millimetres now. And what we find is that certainly sea levels are relatively stable, but around the end of the 19th century, beginning of the 20th century, sea levels started to rise. So what I've done here is plotted 3 of the longest tide gauge records we have in the world. Brest, there's been a tide gauge there for almost 200 years. There's a couple of gaps, particularly around the wall. San Francisco, there's been a record there for well over 100 years. I can't remember where this site is off the top of my head. But what you can see is that at all 3 sites, there's definite evidence that sea levels have started to rise.
It's on the Baltic.
That's on the Baltic, is it?
It's in Poland.
Okay, fantastic, thank you. But what we see is that sea levels are relatively stable, and that's been going on for thousands of years. But we can see this rise, and that rise you can't explain just from sort of natural ice age cycles. Something clearly is happening there. Now what you can see is, again, it's not a smooth rise. Sea levels go up and down. Every year sea levels vary. There's a lot of noise there, but the underlying signal is that rise. And again, I get very fed up with people taking 10 years of data. You take 10 years of data, you can show that things are falling. But if you have a long enough period, you get rid of that noise, you can see the rise.
I have a question, sorry. you very quickly kind of went over the fact that you can't attribute that to the next ice age formation. Why?
If you take similar conditions in the past, particularly when sea levels were higher than today, what we should be seeing really is that flat period continues. So in the past, when there's certainly the last interglacial, we had similar sort of conditions, and sea levels remained stable. So there's clearly some other processes going on, and a bit later in the talk I'll talk specifically about the individual budget that we can add up and try and work out what's happening. Yeah. So we know that sea levels are rising. Now these tide gauge records, there's only a few of them going around the world, but in the last 30 years we've had satellites, and that gives us a true global picture. And what the satellites show, this is a bit old, but they show, again, we've got a definite rise. Over the 20th century, sea levels rose about 1.7 millimetres per year. It's very small, so about 17 centimetres, but that rate has now doubled. Sea levels are now rising at about double the rate in the last 20 to 30 years. But the other thing that's obvious is sea levels aren't just rising everywhere. It's very spatially non-uniform. And this is a map that we get from satellites. The mean is 3 millimetres per year. So if you take the whole world and average it out, sea levels are currently rising about 3 millimetres per year. That's that yellow. But what we see is it's very non-spatially uniform. We see certain regions, particularly here, where sea levels are rising at about 10 millimetres per year, so 3 times the global rate. But equally, we have regions here where sea levels have very slightly fallen. So if you take an average everywhere in the world, sea levels are rising, but some areas are rising faster than others, some areas are not rising particularly fast. In fact, some areas here are actually very slightly falling. So again, it shows you can't just rely on individual sites, you have to really try and understand the whole system. If we take Southampton, this is the long mean sea level record at Southampton that I digitised a number of years ago. But we see that at Southampton, sea levels have been rising at about 1.5 millimetres per year over about the last 70 years. If you just take the last 20 years, again, it's around 3 millimetres. And this is the trend in the high sea levels. So it's about 1.8. It's quite close to the global average. So Southampton seems to be doing something about it. And you can see that most of the UK is that yellow colour, which is the kind of global average. But the important thing is that rate is starting to accelerate. It's getting faster. So what are the 3 main components? We have land-based ice, particularly from glaciers. We have the thermal expansion of water as the water warms and expands. And we have the melting of ice sheets. The Antarctic is not so important because that's not land-based ice, that's in the ocean. Sorry, not Antarctic, the North Pole. But Antarctica and Greenland are really the important things. And what we can do is try and estimate what all of the change that we've seen, what component adds up. So in the last 50 or so years, thermal expansion has accounted for about 38% of that rise has been due to temperature increasing, the ocean's expansion. And actually the largest part has been glaciers. About 40% of this 20 centimetres is seen, 45% is due to glaciers. Greenland has contributed only very small, Antarctica smaller. With that rate accelerating in the last 20 years, actually a much larger component, 58% is due to thermal expansion. Less from glaciers, because actually we've melted a lot of the glaciers now. Greenland has increased slightly. And again, there's still quite a lot of uncertainty with Greenland and Antarctica. But this is just to show you some examples of various glaciers around the world. But what you can see is in 1885, this whole valley was completely covered by a glacier. That's 907, 1930, 1950, 1970, to what you see today. So you can see a huge volume of ice there has made its way into the ocean. This is just one glacier. If you add the many, many thousands, tens of thousands of glaciers, those have contributed quite significantly to sea level rise. This is a bit of a poor picture, but Greenland as well. 1992, 2002, 2007, you can see the area of ice has dramatically increased. Interestingly enough, Antarctica hasn't changed that much. But certainly glaciers and Greenland have contributed. So let's move now quickly to the future. The Intergovernmental Panel on Climate Change, it's about 1,000 scientists from around the world every 7 years, weigh up all of the evidence and come together, and they're just about to start the 6th assessment report. But they predict that sea level rise will be, over the next 100 years, somewhere between 28 centimetres and a metre. That's the likely range. So we think that sea levels could be, I think that lower end is very pessimistic, but I think at least a metre. The UK government, they're just redoing this, and in fact I was working with the Environment Agency on this, but in 2009 they say it could be somewhere between 11 centimetres and 75 centimetres. So there's a lot of uncertainty, and part of that is due to what emissions we're going to submit. It's possible, they had this high-end scenario, it's possible it could be as much as 2 metres, although that's very unlikely. So I think realistically, without a major change, a major collapse of Antarctica, we're looking at about a metre of sea level rise, so 2 or 3 feet. So coming up to my sort of leg level. Now, what's really interesting is that there's a big push. Who of you have heard of the Paris Agreement? Quite a bit of you. So the Paris Agreement was signed by something like 165 countries, and this is the wording. They've sort of promised that we will hold the increase in global average temperature to well below 2 degrees from pre-industrial level, and pursue efforts to limit it to 1.5 degrees, recognising that this significantly reduces climate impacts. So obviously countries around the world, whether they'll do this or not, are trying to sign up to limit sea level to 2 degrees. But what people forget is if we limit temperature to 2 degrees, there'll be lots of benefits. Temperature will be stabilised, lots of climate impacts will be affected. But one of the problems with sea level rise is we're long-term committed to sea level rise. Even if we cut our carbon emissions now, sea level rise is still going to occur for 200 to 3,000 years. And that's because there's a lot of inertia in the system. At the moment, we've only heated the surface of the water. It takes hundreds and hundreds of years for that heat, even if we reduce it now, to transfer. It's the same with ice. Once you start melting ice, it continues melting. It won't just stop. So we're going to see sea level rise, whatever, even if we fulfill this Paris Agreement. So one of the things we've done to look at this is it's very hard to predict sea level into the future. It's very expensive. What we typically use at the moment is very computationally expensive numerical models of the whole world, the climate. They're called GCMs, Global Climate Models. And these have to run on supercomputers. There's only sort of 15 or 20 of these models that run around the world. They're very expensive. So most of them have only been run to 2100 to try and predict what sea levels rise are. But what we've done is developed a very simple model that can run on your smartphone. If you type in CO2 modeler, you can actually download this climate model to your phone and you can run a real-time climate model on your phone, CO2 modeler. But what we do is we represent the whole Earth in a series of boxes. So the whole Earth is just represented in 8 boxes. We have an atmosphere box, a box that represents vegetation, a box that represents the soil and the interactions between them, and 5 boxes that represent the ocean, the surface ocean, right down to the deep, 3-mile deep ocean and the transfer of heat. And all of these boxes are linked by essentially what we've taken is taken a climate model and reduced it to its very, very simplest form. And what we've done is run this model. And what we've done is we've tried to get the model to adjust to certain temperatures. And the reason why this model is, because this model is so simple, we can run it for hundreds of years and see how the climate would respond. So this is the year 2000, where we pretty much know where we're going, but after 2030 we're not sure. So what we can do is we can try and limit to 1.5 degrees, which is the grey line, 2 is that. So that's what the Paris Agreement has tried to link to. At the moment, we're very much on this high emission scenario, which if we continue with that emission scenarios, we're going to increase temperatures by about 10 degrees, which will be catastrophic. But what we've done is we've run the model, including uncertainties, out to 2300 for 1.5 degrees, 2.5 degrees, 3, 4, and then this very high emission scenario. And I think we've already missed the window for 1.5. I don't think that's achievable. But what's really interesting with the sea level projections, even if we cut our emissions and stabilise temperature at 1.5 degrees, sea level will continue rising for hundreds and hundreds of years. Okay, so with 1.5 degrees, sea level rise will reach about a metre. But the really scary thing is, if we continue on our current track, without doing the Paris Agreement, we will get at least 4.5 metres of sea level rise. And what this shows you is we need to start thinking long term. Actually, by 2100, it doesn't make much of a difference. So even if we do Paris Agreement, from a sea level perspective, it only saves about 20 centimetres of sea level rise. But if we act now, we can save at least 3.5 metres of sea level rise. So it just shows you we really do need to make sure this Paris Agreement happens, not for us, but for our great-great-great-great-grandchildren. So just coming to an end then. What I've done is, you guys are the very first to see this. I just produced this yesterday, but this is what's called a climate spiral. And here, this is what happens with sea level. So this is 0 metres, 1 metre, 2 metres. This is what happens with sea level under the Paris Agreement. This is what happens if we continue with our high emission scenarios. And what you can see is it makes a massive difference. You know, we can save about 3.5 metres of sea level rise. And I think, you know, this needs to be on a government level, but it needs to be on a personal level as well, in terms of, you know, each of us committing to try and do our own little part. Now, if all of the world's ice melted, there's about 80 metres of sea level rise in there, and this is what the UK would look like. Now, we would be gone. Norwich would be gone. Now, obviously, this can't happen, certainly in the next 100 years, because you just can't physically melt ice that fast. But potentially, if that was to happen, that would what the UK would look like. So just in the last few minutes, what can we do about sea level rise? The UK has developed something called shoreline management plans, where they've divided the coast into stretches and tried to work out some of the options that we can do. And sadly, we're going to have to make some difficult choices. It's very, very expensive to defend the coast, and we simply can't defend the coast everywhere. And what we'll have to do is some sort of cost economic benefit, and say, you know, is it really worthwhile spending millions of pounds if we're only protecting 2 or 3 houses? And unfortunately, we're going to have to make some decisions in some stretches of coastline to do no active intervention. This is where if you have a house on the coast, there might be a flood defence there, there might not be. Whatever the situation is, we're just going to have to say, look, we're going to do nothing. It sounds harsh, but we don't have enough money to defend the whole of the UK. So one of my colleagues in Germany just did a cost-benefit analysis, and he thinks it only makes economic sense to defend about 8% of the world's coastline. And those coastlines where you've got major cities. So unfortunately, there's going to be some...
Okay, that's fair enough if you compensate the people who are actually going to lose out, but we're not doing that. And I was at a meeting yesterday in London where we're actually discussing that very topic, and at the moment, the government in this country isn't prepared to compensate individuals. We're seeing that, we've just raised it, seeing on television in Norfolk and other places, where people are losing their homes, they're still paying their mortgages. So if you make that decision, you've also got to temper it with something else on the other side.
What's your name?
Frank Green.
Okay. I'm not making that decision.
No, I know you're not.
I wouldn't want to make that decision.
And we weren't making it, but we're
no.
trying to work with
Yeah.
DEFRA as an agency.
Who do you work for?
New Forest National Park.
Okay, yeah. This is really sad. I don't like talking about this. I wouldn't want to be making those decisions, but unfortunately the sad reality is we just don't have enough money to defend the coast everywhere.
I agree,
Yeah.
but I think you've got to compensate people.
Yeah.
The few people it's going to affect, you can spend whatever it costs to buy their properties and compensate them.
Yeah.
Similarly, farmers may need to be compensated if they lost their farm there,
Yeah.
but we're not doing it.
I know.
So it seems to be a very unfair situation.
No, I 100% agree.
But there we are.
Yeah. I mean, the sad thing is, you know, I'd love to live near the coast. I'd love to live in a house on the beach. But yeah, no, it's...
Well, soon.
but you're right, you know, but the sad truth is the government probably doesn't have enough money to compensate everyone. So
Well, we didn't think that was the case.
Okay.
It's a matter of choices. You can
Yeah.
choose to spend money here or money there.
Yeah.
If you're choosing not to defend the coastline, you may have resources where you can actually put it somewhere else.
The other thing which I'll come on to in a minute as well is in fact I'll come on to that in a second. So this is the first thing we are going to have to make, not me, but the government, whoever's in charge, is going to have to make really tough decisions that will affect lives, and people should be compensated. I agree. It's just to do no intervention. There's other stretches of coastline where we're going to hold the line. Where in the UK are we definitely going to hold the line 100%? London. There's no doubt about it. London brings in so much investment. So there is parts of the coastline we're going to hold the line, but we can only hold the line where it makes economic sense to do that. Okay? And we can hold the line through things like the Thames Barrier, through millions of pounds of investments in flood defences. There's parts of the coastline where we're going to have to do managed retreat. And to me, so I'm working on one site up in the Bristol Channel, and this tends to be farmland. So around the UK, there's been 40 such sites. So this is an example here. What they've done is, this whole area of land, they were spending millions and millions of pounds defending the coast. So this is the coastline, this is the River Parrett, this is just north of Bristol near Sturt Peninsula. They were spending hundreds of millions of pounds defending what was just farmland. And it just didn't make any economic sense to do so. So what they did is they bought the land off the farmer, compensated him very well for that, and they said, let's just let this land flood. This land would have been a natural salt marsh anyway, so they put a breach in here, and they designed a creek system just to get the water going, but now all of this land's flooding. Now the good thing is, when a storm surge happens, rather than the water going all the way up the river and flooding Bridgeport, there's now this extra space where the water can go. So it has benefits as well. Not only that, but it creates beautiful coastal habitat. They've made paths here, hundreds of people can go walking there, see birds. So more and more, over the next 100 years, the government have just released a big report on this, we're going to move away, you probably know more about this than me, we're trying to move away from hard flood defences to more natural-based solutions. Nature is always the best at protecting itself. Things like mangroves, things like salt marshes, they absorb the wave energy. The fact that we've destroyed salt marshes, put walls there, in the long run it's actually made the situation worse. So we're going to have to go towards more natural solutions. The other thing we can do is say, oh, screw you, sea level rise, let's advance the line. Who cares, let's go out to the line. And this is happening in Dubai. They've done that, they've built the island, they've built the palm, and in the Maldives they've built an entire island. This is an entirely man-made island. The other thing we can do, and I really want to see us doing this, is try and adapt. I think we're as a humankind, we do some fantastic things, and I think we've got all of the money, all of the ingenuity to be able to adapt, to build floating houses, to build bridges. This bridge actually floats, it rises with sea level rise. And actually just to live with flooding. So in Bangladesh, people want to live on the floodplain because it's very fertile. And as long as you have a good warning system, they've built a number of these structures here, where as long as people, they're very poor there, but they want to live on the land, it's very fertile. But if you've got a good flood forecasting service that says, look, 2 or 3 days a flood's going to happen, you move all of they don't have very much there, they move all of their cattle, livestock to this level, they live up on that level, their house gets destroyed, but 3 or 4 days later they're alive, all of their properties are there, they go back, build another temporary structure, they can benefit from those rich, fertile soils. So it's kind of this living with water. And I think we need to do that in our cities. We need to build underground car parks that, when a flood's happening, we can let those flood, let the water go there rather than doing it. So that is me finished off. So that's just a whistle-top tour through sea level rise and some of the things we can do about it.
So unlike before, I'll go straight into questions and answers, but before I forget, people at the back, can they see what's on the bottom of the screen as the image is at the moment? Right, okay. Because I was thinking about extending upwards a bit, it might work, it might not. Question please.
So if anyone needs to go, please just feel free to make your way out. I won't be offended in any way. Please tell me your name when you answer the question, and ask the question as well. That'd be useful.
I'm Prof. So you didn't mention at all. You mentioned ice masses, but you didn't mention at all the fact that as the temperature of the oceans rises on average, the amount of moisture in the air increases, and this causes white clouds to form, which reflects the sunlight and cools the earth.
cools the Earth.
Because you get the clouds, and the clouds will reflect, and as you have more, as the temperature rises,
Yeah.
then you get more rain. Now I know they look white from down here,
Yeah,
but
sure.
from the upper atmosphere,
Yeah.
they look white or silver.
Okay.
And high clouds will reflect the sunlight back out.
Yeah.
So as you get, I mean, obviously it won't be habitable, but like, it's not going to reach a temperature. It's going to reach a temperature which might be quite high, I don't know, where the moisture in the atmosphere causes sufficient change in the reflectivity of the surface of the Earth that the sunlight isn't absorbed as much.
I'm not a climate scientist, so I know absolutely nothing about that. I'm afraid my expertise is very much on the sea level side of things, so I wouldn't even.
But it must be a factor, because you've only taken into account the melting of the ice. You've not taken into account the volume of water which is taken up out of the sea.
I mean, all I can say from my expertise is sea levels are rising. They're continuing to rise. We can work out which different components. One of the really interesting things that I didn't mention is actually water. We've got a satellite up there at the moment called Grace where we can monitor water. And what we are finding is that more groundwater is making its way into the oceans faster. That's why there's hills. But actually we find that the building of man-made dams has actually slowed sea level rise down slightly because so many more dams have been built, that water's being stored on land. But that typically is a small component. But yeah, I'm afraid I don't know. I'm not an atmospheric scientist. But you do get feedbacks in the climate system. So one of the key feedbacks is ice albedo. The more ice that melts, the less white space there is, the less energy that's absorbed. And that would actually do the opposite. That would speed up the warming process. But if you want, I can put you in touch with an atmospheric scientist who probably will be able to answer that. I tend to know a lot about the sea, but not a lot about the atmosphere. So.
Jackie, I'm not a scientist of any sort, but I remember reading somewhere that the moon is gradually moving away.
Yes.
So that's going to affect waves, the pool in the centre, which means that the pool will get less from the land, so sort of flatten it out a bit more as the moon moves away. Because I understand it's moving away at quite a dramatic speed.
It's not dramatic, it's quite small, but over thousands of years it adds up. So what happens is that this doesn't massively affect mean sea level. It slightly affects the geology. One of my colleagues at Bangor University has just written a paper on this, and actually I'm being interviewed on Radio 4 on Friday afternoon in their science program. So if you listen to that, I will be talking all about tides on Radio 4. I'm being recorded on Friday. When's the science? I don't know when it's going to be broadcast, but send me an email and I will. So the tides are changing. What's happening is all of this, the energy of the moon and sun is put into the ocean, that energy gets dissipated, and over time that's causing the moon to get further and further away. But it's very small on our sort of timescales that we're interested in.
Can you remind us, if all the ice got melted, how much the sea level will rise?
It's estimated about 80 meters. There's Greenland on its own has about 8 meters of sea level rise. So if all of Greenland melted, that would be 8 meters. And Antarctica is somewhere between 65 and 75 meters of sea level rise. Yeah. What's really interesting, there was an article the other day that shows that Antarctica is actually gaining ice, which they think has been preventing sea level rise. But what we're really concerned about with Antarctica is a major collapse of the ice sheets. What happens is the warmer water is getting under the ice, and if those ice sheets collapse, even though they're on the ocean, that might allow more ice from the land to flow in the sea. So there's major concerns that if that collapses, sea levels could rise several meters quite quickly. Yeah.
Is that anything to do with an article I've read recently about the Gulf Stream current slowing down? There's prediction of wind.
Yeah, so there's been...
Is that muddying the water? Is that complicating the issue? Okay. Yeah.
So there's been 2 papers in Nature, and I know the authors of both of those papers. And Nature's the best journal in the world. They're very high-profile papers, and both of them show it's called the AMOC, the Atlantic Meridional Ocean Circulation, of which the Gulf Stream is a part of. And the Gulf Stream basically means that our climate here is warmer than in Iceland. But over hundreds and thousands of years, that changes. That won't affect sea level so much, but it will have huge implications on our weather patterns and our temperatures. Interestingly, it does affect sea level on the coast of America. Because what happens is, if this is the coast of America, the Gulf Stream actually causes sea levels to be lower, because you've got this big current going. It actually forces water to be slightly higher in the Atlantic and lower along the coast of America. And what happens is, as that current slows, you get less geostrophic flow. So actually what we are finding is that sea levels are rising faster along the American coastline as a result. But that tends to be, in terms of, that doesn't affect global sea level very much, but it does have this kind of regional hotspot. Yeah.
What sort of temperatures would you need to achieve to get full ice melt?
You wouldn't in hundreds of years. It's the same, you know, if you have an ice cube, even if you put the temperature in the room, double it, that ice cube doesn't instantly melt. It takes hundreds and hundreds of years. And if you think the ice in Greenland is 3 kilometers thick, so there is various projects. So one of my colleagues in the University of in Australia, ANU, Australian National University, he thinks I can't remember the. Send me an email and I'll give you the precise figure. But it's 10 degrees plus, but sustained over hundreds of years.
One of my concerns about this global warming is that what percentage of human CO2 emissions as compared with natural, what is the percentage of our input to it?
Again, I'm not really an expert when it comes to kind of the atmospheric side of it, but from what I've read is since 1970, it's a very large percent. Before 1970, so part of the reason why I wanted to show you that past stuff is sea level varies naturally. It varies by hundreds of meters naturally, but it also varies over the last 100 years. Sea level can vary by 5 to 10 centimeters purely naturally, by changes in El Nino oscillation, by changes in wind patterns, by changes in atmospheric pressure? Atmospheric pressure. These are all natural effects, but I would say since the 1970s, I would say at least 80 to 90% of warming can now be attributed to anthropogenic.
Right. Well, going on to that, even if we in the Western world reduce these limits, the other countries are actually coming up far larger than us, and they will actually negate by many times the what we will save. So,
well, UK is getting lower and lower down the list. India, China's almost overtaken America at the moment,
and South America.
South America is up there as well. Alejandro will know that. The thing that I'm concerned about is a few months ago I met with community leaders from the Solomon Islands. And again, I feel very sorry, the Maldives as well. They have the lowest emission rates in the world, and yet they're the ones that are feeling the effects of sea level rise first. Just to say as well, my father's a climate skeptic. He doesn't believe in climate change. But one thing I like with sea level rise is whether you believe in climate change or not, it doesn't matter. Sea levels are rising. They've been rising for 150 years. They show no signs of stopping. They're getting faster. So whether you believe in climate change or not, we as mankind, we've gone and built mega cities on the coastline. There's 139 cities with populations greater than 1 million on the coast. So whether you believe in climate change or not, sea levels are rising. That's the fact. Yeah.
Andy Russell from Southampton Archaeology Unit. We've got plenty of evidence that sea level's risen by 5 metres in the last 5,000 years. So where does it's been level for 7,000 years come from?
There's two components to sea level rise. There's absolute sea level rise, which is change in the ocean. There's there's relative sea level rise. And in fact, I ran out of time, so I skipped this. So you have to be very careful with this. So satellites measure absolute sea level, okay? And that is just changes in the volume of the ocean. Tide gauges measure relative sea level, and that's both sea level rise, but changes in the level of the land itself, okay? And one of the things with the UK is we have glacial isostatic adjustment. So we think the land is stable, but the land is moving. And think of this like a giant, my wife, when we moved into our new house, bought a foam mattress. Think of this like a foam mattress. You dive onto a foam mattress, it sinks, you get off. If it's a good foam mattress, it will take hours to creep back up. And what we find with the UK is, in the last ice age, 20,000 years ago, almost all of northern England was covered in ice. And even though that ice has melted, it's taken tens of thousands of years for the UK to respond. So think of it, it's covered in ice, even though that ice melting, it takes a long time for that foam mattress to rise. So what we find is that northern England is actually rising because it was weighed down by the ice that's coming up. So northern England is rising by about 1 millimetres per year. This is just the land. Southern England is actually sinking. And what we find is this glacial isostatic effect is massive in parts of the world. So actually, if you look at Iceland, if you look at Stockholm, sea levels are actually falling in Stockholm. Now, sea levels themselves aren't falling, it's the land is rising higher than sea levels are rising, so it looks like sea levels are falling. So certainly there's a lot of archaeology evidence that sea levels changed by 5 metres, but that's not absolute sea level, that's relative sea level, which includes these.
So it can be very localised.
And that can be very localised.
It is very localised. And Solent, because we're in the Hampshire Basin, the Hampshire Basin is even much more complicated because the basin itself is prone to sinking. So if you look at the gravel terraces, they don't match across the south coast here.
Yeah.
So in fact you can't say gravel terrace 10 here, it's actually at a different height.
Yeah.
So you have the localised problem that Andy's just saying, it's very localised.
So
combined with the isostatic adjustment.
So one of the key localised land subsidence is groundwater extraction. And so lots of cities, Bangkok is a perfect example. Everyone in Bangkok in the 50s had their own well in their garden. And they were sucking up groundwater, and the whole of Bangkok has sunk by 2 metres. Now, people in Bangkok are worried about sea level rise. Sea level rise doesn't mean anything. This land subsidence is 20 times the height of sea level rise. And that's not climate change, that's human, but not climate related. So again, we did this piece of work here, but all of the major cities, particularly those on deltas, Tokyo has sunk by 4 metres. Where else have we got? But Bangkok, and you can see it in Bangkok. So these telegraph poles used to be on land, now they're in the ocean. So yeah, so again, unpicking these things is quite difficult. And what we find with Bangkok is that sea levels are rising, but after the 1950s, they massively accelerated. Now again, this is why it's really important to interpret the data. People thought, okay, that's climate change, but that's not. Actually, that was just land subsidence, and you have to try and factor those effects out. But in Bangkok, they had to put they were so worried about this as causing way more problems than climate change that they've put a law in place that people can't have wells in their own garden, they can't extract groundwater, they get fined a lot of money if they do now. And that seems to have stabilised the problem. But this also happened in New Orleans. Part of the reason why New Orleans was so badly flooded during Hurricane Katrina is that the land has subsided so much. So all of these things are additional factors to take into account. You know, people get obsessed with climate change. Climate change is important, but there's lots of other things that have, and sometimes can have larger effects than climate change. And this is a perfect example.
Question on surges. I've not been able to find an answer to this, but if you've got a surge coming in off the Atlantic, so Newlyn, it's 0.5 metre, so above the sea level it should have otherwise been astronomically. And let's say it's a neap tide, relatively low, and it comes up and we, round the Isle of Wight, get a certain level of surge, which tends to be a bit higher. For exactly the same circumstances, the same wind and that, but on a spring tide, that bit higher, would the surge for a 0.5 metre coming in at Newlyn be higher than the case with a neap tide? And extending on from that, with sea level change, with overall levels of being that much higher, with more depth of water for surges passing over, everything else being the same, with decades in the future, would the penetration of the land be higher than it would have been?
So interestingly, so these are what we call indirect effects, and they're very complex. We call them tide surge interactions, and they involve these non-linear effects. They're very complicated. But essentially there's two aspects to it, and you can show this by, if you just get two containers and blow over it, wind is more effective at rising water when it's shallow than when it's deep. And this is why the North Sea is seen as the perfect storm surge basin, because it's so shallow. And this is why we get much bigger storm surges in the North Sea compared to the English Channel, which is deeper. And what happens on the tide is, if a storm occurs on a neap tide, often your storm surge is actually slightly bigger than if it occurred on a spring tide. Not the total water level, just the... And you get this with hurricanes very much, is that if a hurricane at low water creates more of a storm surge than at high water, not the total water level, just the meteorological induced component, you also get something which is, a storm surge travels as what's called a shallow water wave. And it means that its speed is dependent on water depth. And there's an equation, root GH, so the speed of a wave is gravity square rooted times by the height. And what happens is actually when you raise your water, your storm surge can actually travel faster because it's deeper. So what's really interesting is, as sea levels rise, it should actually very slightly reduce storm surges. Because your water's deeper, but then again you have the effect that when sea levels rise, waves can break closer to the shore than before, because waves get to a certain water depth and break, and as sea levels rise. So these are all, they're called indirect effects. There's a lot of been work done on them, but they're quite small. They don't make a mass. We're talking centimeters, not meters.
So your advice is everyone move to Scotland.
if I could afford to live on the coast, I probably would live on the coast. And it's a tough one. The problem is legacy. If you could we've gone and built in all the wrong places. You go onto Google Maps and you look at Winchester. Winchester is in a river floodplain. The rivers are supposed to flood. It's good for the land. Flooding is good. It brings... the problem is we've gone and built in the wrong places. The problem is we can't change that easily. I think the government should be stricter. I think there should be stricter rules in terms of where you can build. I also think it should be law now that if you build in the floodplains, your house has to be on stilts. The plugs have to be at a certain level. We have to live with it. So yeah, the problem is that legacy really. But yeah.
If the Gulf Stream moves, then Scotland will become permafrost. Does that mean it'll sink again?
Well, the funny thing is a couple of years ago, I took a taxi. I was going to a conference somewhere. I took a taxi up to Heathrow, and my taxi driver was saying to me, I'm not going to drive a taxi anymore. I've actually started an air conditioning business. He said, I'm still working while I get this off the ground. And he said, obviously, climate change is happening. More people are going to want... he was generally serious. He had started this business. And I didn't want to say to him, but I said, actually, climate change doesn't mean that temperatures are going to rise everywhere. Globally, they'll rise. But actually, in UK, it could be a shutting down of the Gulf Stream, which actually, climate change could actually drop our temperatures. I didn't tell him that.
but air conditioning is one of the things that, Americans, it's a real problem. Is actually one of the major causes for consumption of energy. Yeah. Hence,
well, I hated it. So I lived in Australia for 3 years. I had an office with people in, and the air conditioning didn't work so well. I was freezing at work. I would go in midwinter, 35 degrees outside. I was in a jumper. It's just such a waste of energy. And but yeah. Should I take 2 more questions, and then after that, I'm happy to speak to anyone individually.
In the States, it's quite common for them to literally move house. Has anyone been able to jack up and then put on floats and build up dolphins on a brick-built house?
They've done it in Chesapeake Bay.
In where?
Chesapeake Bay, lots of streets. The problem in the States is that, in fact, this house, I think I'll show it right at the end. This house here has been destroyed about 10 times in the last 20 years. But that house always gets government aid, federal aid, and they just go and build it again in that exact same. I'd love to live there, who wouldn't? But to me that's criminal. If your house floods more than 3 times, there should be a rule, it should be 3 times and then you're not getting any more aid. But it's a hard decision, one of the things I learned is, it's easy to talk about these things, but if you've been flooded, it's a horrendous experience, and I think we do need to make this personal as well. And if I lived on the coast, I probably wouldn't want to move, and I'd be very upset about paying my mortgage off if my house had gone off the cliffs. So, yeah.
There's some examples in the Thames Valley with very rich people who have actually done exactly what you've said.
Well,
Brick-built structures have been completely underpinned, and then they're actually on jacks, hydraulic jacks, that allow them to be lifted above flood level.